Welcome to the AI Research Roundup. I'm your host, Alex. Today is May 9th, 2025, and we're looking at an interesting ICLR conference paper titled MLE-bench, Evaluating Machine Learning Agents on Machine Learning Engineering, published just over 3 months ago on January 22nd, 2025. This paper introduces MLE-bench, which is a new benchmark, essentially a standardized test, designed to see how well AI agents, these are AI systems that can act on their own, can handle complex machine learning engineering tasks, or MLE tasks, all by themselves. Machine learning engineering is really about the practical side of building and running these AI systems. Alright, so this figure really lays out how MLE-bench operates as an offline environment for these AI agents. You see, each competition within the benchmark provides the agent with a description, a dataset, which includes files like "train.csv" for the agent to learn from, and "test.csv" to make predictions on, and a leaderboard from Kaggle. Kaggle is a well-known platform for data science competitions. The agent then processes this, trains its model, and produces a submission. This submission is then evaluated by a local grader, which assigns a score and compares it against human performance benchmarks from the actual Kaggle leaderboards, potentially awarding medals. Okay, building on how MLE-bench works, this next figure shows us actual examples, or trajectories, which are the sequences of actions an AI agent takes when trying to solve a problem. It compares 3 agents, all using the GPT-4o model, but each supported by a different system known as a scaffolding framework, MLAB, Open Hands, or AID. What's really interesting is how the ADE framework, specifically built for these kinds of machine learning engineering challenges, guides the agent to design a solution. For instance, by planning to use test time augmentation, a technique to improve predictions by testing varied inputs, and a special focal loss function, which helps the model focus on the trickiest examples. Now, to really understand what it means for an agent, like the one using the AID framework we just saw, to earn those medals, this table clarifies the scoring. It shows the thresholds for winning bronze, silver, or gold medals, which MLE-bench directly adopts from actual Kaggle competitions. You can see how these thresholds change, depending on the number of teams. For instance, in smaller contests with 0 to 99 teams, a bronze is awarded to the top 40%, while for gold in very large competitions with over 1,000 teams, it's the top 10 plus a small adjustment. This provides a clear, human benchmarked way to rate agent performance. So building on those medal thresholds, this table presents the actual results, showing average scores from multiple runs. It details how different AI models, like O1 Preview or GPT-4o, perform with various scaffolding frameworks, AID, MLAB, or Open Hands. These experiments were repeated using different seeds, which are like starting points for randomness, to ensure the reported average results are reliable. It's clear the AID framework is a big help. For example, GPT-4o with AID earned medals in 8.7% of tasks, but the O1 Preview model, also with AID, really stood out, achieving medals nearly 17% of the time. Following those average scores, this figure explores how giving the agents more chances, or attempts, influences their success. The vertical axis shows "insolade my amis excess," which is the percentage of medals achieved when the agent is allowed K tries at a task. We see 2 models here, O1 Preview and GPT-4o, both with the AID framework. More attempts clearly boost performance for both. For instance, O1 Preview nearly doubles its medal rate from its first attempt to its 8th. Interestingly, GPT-4o needs about 6 attempts to reach the same medal rate that O1 Preview achieves on its very first try. Alright, so we saw that more attempts can boost success. This figure now explores another factor, how much time the agent gets for each attempt. It shows the percentage of competitions where the GPT-4o model, paired with the AID framework, wins a medal, plotted against the number of hours it's allowed to work. Performance clearly improves with more time, especially early on. The medal rate jumps significantly in the first 20 hours and continues to rise, reaching almost 12% by the 100-hour mark, up from about 8.7% at 24 hours. So, giving the agent more thinking time per try generally pays off. Okay, so we've seen that more thinking time generally helps these agents. But to really appreciate their performance, it's good to understand the challenges they're up against. This figure breaks down the MLE-bench, showing the 75 competitions spread across 15 diverse problem categories, like image classification or tabular data tasks. The colors in the bars indicate the complexity, from low, meaning an expert human might solve it in under 2 hours, to medium and high, which could take over 10 hours. This variety, with over half the tasks being medium or high complexity, shows MLE-bench really tests these agents thoroughly. So that diverse set of challenges really establishes MLE-bench as a robust test. In essence, this research demonstrates that current AI, especially when combined with effective scaffolding, those crucial support frameworks for problem solving, can achieve meaningful results on complex machine learning engineering, or MLE, tasks. The O1 preview model, for instance, showed remarkable capability. While limitations like debugging persist, MLE-bench itself is a valuable contribution for tracking progress in autonomous AI. That's our roundup for today. Thanks for joining me, Alex.